So we've got chapter 5 we're looking at. It's cameras and film. We've got in chapter 1, we describe the pinhole camera model that's commonly used in computer graphics. This model is easier to describe than simulate. It neglects important effects physical lenses have on light passing through them. For example, everything rendered with pinhole camera is in sharp focus, a state of affairs not possible with a real lens system. Such images often look computer generated for their perfection. More generally, the distribution of radiance leaving a lens system is quite different from the distribution entering it. Modeling this effect of lenses is important for accurately simulating the radiometry of image formation. Camera lens systems introduce various aberrations that affect images that they form. For example, vignetting causes darkening towards the edges of images due to less light making it through to the edges of the film or sensor to the center. Lenses also cause pincushion or barrel distortion, which causes straight lines to be imaged as curves. Although lens designers work to minimize aberrations in their design, they can still have meaningful effect on images. Yeah. And interestingly, we put a lot of effort into simulating that imperfect nature. That's interesting. The chapter starts with a description of the camera interface, after which we present a few implementations, starting with the ideal pinhole models. After light has been captured by a camera, it's measured by a sensor. While traditional film uses a chemical process to measure light, most modern cameras use solid-state sensors that are divided into pixels, each of which counts the number of photons that arrive over a period of time for some range of wavelengths. Accurately modeling the radiometry of how sensors measure light is an important part of simulating the process of image formation. To that end, all of PBRT's camera models use an instance of the film class, which uses the basic interface for the classes that represent the images captured by cameras. We describe two film implementations for this chapter, both of which use the pixel sensor class to model the spectral response of a particular image sensor, be it film or digital. Film and sensor classes are described in the final section of this chapter. The 5.1 is the camera interface. So I'm not exactly sure what this tagged pointer thing is, but they have some stuff about it. It's how it handles polymorphic types. It's a pointer to an object of a known type, takes a pointer of an object to a known type, and uses excess bits on the pointer to encode the actual type. All right. Because it doesn't have to index very many of them or something. Let's get some extra bits. Something. Anyway, okay. Using this approach to dynamically dispatch interface method calls for the correct implementation based on the actual type of camera. As usual, not include the implementations of those methods in the book here. Camera is defined in the file base/camera.h. The first method they must implement is generate ray, which computes the ray corresponding to a given image sample. It's important that the direction component of the ray be normalized. Many other parts of the system will depend on this behavior. If for some reason there is no valid ray for the given camera sample, then a P standard optional return value should be unset. Okay. Sampled wavelengths for the ray are passed as non-const reference so that the camera can model dispersion in the lenses, in which case only a single wavelength of light is tracked by the ray when the generate ray method will call. Sampled wavelengths terminate secondary. The camera sample structure that's passed by generate ray, passed to generate ray, holds the sample values needed to specify a specify camera ray. The p-film member gives the point on the film to which the generated ray should carry radiance. Point on the lens that this ray passes through is in p lens. Interesting. It's talking about modeling realistic lenses here, and doesn't pass through at a single point. multiple interfaces. Anyway, thank you.
Weren't you doing something with camera stuff?
Still pending. Yes, I actually had. All right. Well, we'll talk about it later. Cracked that problem yesterday. It was actually pretty cool. Yeah. Finally, filter weight member variable is additional scale factor is applied when the ray's radiance is added to the image stored by the film. It accounts for the reconstruction filter used to filter image samples at each pixel. This topic is discussed in 5.4.3 and 8.8. Sorry, let's get some stuff here. Yeah, so I guess, yeah, time is also relevant if you're doing camera in motion. You want to do some sort of animation or motion blur. So camera ray structure that's returned by generate ray includes both ray and spectral weight associated with it. Simple camera models have the weight at a default value of 1. More sophisticated ones like realistic camera return a weight that's used in modeling the radiometry of image formation. 5.4.1 contains more information about how exactly this weight is computed and used in the latter case. Okay, so camera ray definition, we've got the ray, and then the spectral weight, spectral effects. Camera must also provide an implementation of generate ray differential, which computes the main ray like generate ray, but also computes corresponding rays for pixels shifted 1 pixel on X and Y on the film plane. This information about how camera rays change as a function of position on the film helps give other parts of the system a notion of how much of the film area a particular camera ray's sample represents, used for anti-aliasing text relookups, things like bitmaps too. Generate ray differential returns an instance of camera ray differential of the structure which is equivalent to camera ray, except it stores a ray differential. Which I'm not sure how they're represented. Okay. So the origin direction as like distribution kind of thing. Or
I think rate differential is just for textual lookup, where
yeah.
you want to do some anti-aliasing kind of stuff.
Cool. Okay. So camera implementations must also provide access to their film, which uses other parts of the system to determine things such as the resolution of the output image. Okay. Just like real-world cameras, PVRT's camera models include a notion of a shutter that opens for a short period of time to expose the film to light. One result of this non-zero exposure time is motion blur. Objects that are in motion relative to the camera during the exposure are blurred. Time is yet another thing that is amenable to point sampling and Monte Carlo integration. Given an appropriate distribution of ray times between the shutter open time and the shutter close time, it's possible to compute images that exhibit motion blur. I wonder if they model like the process of it opening or something that's like has some point in time where it's closed and then it opens over some period. It's interesting. Sample time interface method should therefore map to a uniform random sample in the range 0 to 1 to a time when the camera shutter is open. Normally, it's just used to linearly interpolate between the shutter open and close times. Okay, it's probably not. It's just, yeah, it's just step function. Last interface method allows camera implementations to set fields in the image metadata class, specify transformation matrices related to the camera. Like an EXIF thing. Interesting. If the output image format has support for storing this sort of auxiliary information, be included in the file image that's written to disk, like a real camera. That's interesting. You can set like the f number and focal length, things like that. That's interesting. Before we start to describe the implementation of PBRT's camera models, we'll define some of the coordinate spaces that they use. In addition to world space, which was introduced in 3.1, we'll now introduce 4 additional coordinate spaces. So we've got object space, camera world space, and rendering space. So object space is where the coordinate system in which geometric primitives are defined. So, for example, spheres are defined to be centered at the origin of their object space. Okay. World space is, while each primitive may have its own object space, all objects in the scene are placed in relation to a single world space. World from object transformation determines where each object is located in world space. World space is the standard frame that all other spaces are defined in terms of camera space. Cameras are placed in the scene at some world space point in a particular viewing direction and orientation. Camera defines new coordinate system with its origin at the camera's location. The z-axis of this coordinate system is mapped to the viewing direction. The y-axis is mapped to the up direction. That camera stuff that I've been playing with has mostly been doing things in this kind of camera, like optical system kind of space. So camera world space is like camera space, the origin of the coordinate system at the camera's position, but maintains the orientation of world space. So it adds directionality. So it's not necessarily just looking down the z-axis. Rendering space is the coordinate space into which the scene is transformed for the purposes of rendering. It may be world space, or camera world space. So it's as appropriate, I guess. Renderers are based on rasterization traditionally to do most of their computations in camera space, based on rasterization. They typically do the computations in world space. Triangle vertices are transformed all the way from object space to camera space before being projected onto the screen and rasterized. In that context, camera space is a handy space for reasoning about which objects are potentially visible with camera. For example, if an object's camera space bounding box is entirely behind the z=0 plane, and the camera does not have a field of view wider than 180 degrees, the object will not be visible. So, conversely, many ray tracers, including all versions of PBRT prior to this one, render in world space. Camera implementations may start out in camera space when generating rays, but they are transformed into world space, where all subsequent ray intersection and shading calculations are performed. The problem with that approach stems from the fact that floating point numbers have more precision close to the origin than farther away from it. If the camera is placed far from the origin, there may be insufficient precision to accurately represent the part of the scene that it's looking at. And that is real. That's a very tangible thing. I've learned more about numerical precision and that type of stuff the past year than I ever wanted to know. Anyway, so 5.1 illustrates the precision problem of rendering in world space. Scene is rendered with the camera and objects as they are provided in the original space specification, which happen to be in the range of plus or minus 10 in each coordinate in world space. 5.1b, both the camera and the scene have been translated to a very large number, moved to a place where they have a lot less precision. But they should be the same, but much less precision is available in the second viewpoint to the extent that the discretization of floating point numbers is visible. So the original then translated in world space, it's some interesting blockiness happening where you're, okay, that's interesting. That's fairly bad. And then I guess compensated, however they're compensating for it. So as originally specified, scene is within 10 units of the origin. rendering the scene in world space produces the expected image. Just as an aside, don't ever try to index into a buffer with floating point numbers. If you go above 2 to the 27th, that's where it starts only hitting every other element. It's pretty cool. It sucks. Trying to find why that's happening. Yeah, anyway, it was just an implicit casting issue. Anyway, if both the scene and the camera are translated 1 million units from the origin, the scene is rendered in world space. There's significantly less floating point precision to represent the scene, giving a poor result. If the translated space is rendered in camera world space, much more precision is available than, and the geometric detail is preserved. However, the viewpoint is shifted slightly due to loss of accuracy represented in the representation of the camera position. So, what's the, is there A between A and C? It's supposed to be different. Translated scene is rendered in camera world space. Viewpoint has shifted. Guess we'll have to take their word for it. Rendering in camera space naturally provides the most floating point precision for the objects closest to the camera. Scene in 5.1 is rendered in camera space, translating both the camera and the scene geometry by 1 million units has no effect. The translation is canceled out. However, there's a problem with using camera space while ray tracing. Scenes are often modeled with major features aligned with the coordinate axes. Consider an architectural model where the floor and ceiling might be aligned with planes on, Y planes. Axis line bounding boxes of such features are degenerate in one dimension, which reduces their surface area. Acceleration structures like the BBH introduced in Chapter 7 are particularly effective with those bounding boxes. In turn, if the camera is rotated with respect to the scene, axis line bounding boxes are less effective at bounding such features, and rendering performance is affected. So in 5.1, increased by 27%. Okay, so degenerate bounding boxes are, oh, okay. This, yeah, because it just goes to 0 on that dimension. Rendering using camera world space gives us the best of both worlds. Camera is at the origin, and the scene is translated accordingly. However, the rotation is not applied to the scene geometry, thus preserving good bounding boxes for the acceleration structures. With camera world space, there's no increase in rendering time, and higher precision is maintained, as you see in 5.1c. The camera transform class abstracts the choice of which particular coordinate system is used for rendering by handling the details of transforming among various spaces. Camera implementations must make their camera transform available to other parts of the system. So we will add one more method to get the transform out. Camera transform maintains two transformations, one from camera space to rendering space, and one from rendering space to world space. In PBRT, the latter transformation cannot be animated from rendering space to world space. Cannot be animated. And the animation in the camera transformation is kept in the first transformation. Camera space to rendering space. This ensures that a moving camera does not cause static geometry in the scene to become animated, which would in turn harm performance. Camera space to rendering space. The rendering space to world space is not. So I guess you just have fewer transforms to apply to like your geometry and stuff like that. They can just be applied once or something. Camera transform constructor takes the world from camera transform as specified in the scene and decomposes it into two transformations described earlier. The default rendering space is camera world, although this choice can be overridden by the command line function option. Okay. For camera space rendering, the world from camera transform transformation should be used for world from render and an identity transform for render from camera transform, since those two coordinate systems are equivalent. However, because world from render cannot be animated, implementation from takes from world from camera transform. Implementation takes the world from camera transform at the midpoint of the frame and then folds the effect of any animation in the camera transform into render from camera. For the default case of rendering in-camera world space, the world from render transformation is given by translating to the camera's position at the midpoint of the frame. Okay, for world space rendering, world from render uses the identity transform. Once world from render has been set, whatever transformation remains from world from camera is extracted and stored in render from camera. Camera transform class provides a variety of overloaded methods named render from camera, camera from render, and render from world. Transforms points, vectors, normals, and rays among the coordinate systems it manages. Interesting. Other methods return the corresponding transformations directly. Their straightforward implementations are not included here. So we've got the camera base class. So all the camera implementations in this chapter are somewhat common functionality factored into a single class, camera base, from which all of them inherit. Camera base, as well as the camera implementations, are defined in the camera.h and camera.cpp. Okay, so we got the structure that takes parameters. One of the most important is the transform, transformation that takes places the camera in the scene, represented by a camera transform, and is stored in the camera transform member variable. Next is a pair of floating point values that give the times at which the camera's shutter opens and closes. Film instance stores the final image and models the film sensor. Last is a medium instance, represents the scattering medium that the camera lies in if any medium is described. Or sorry, if any medium is described in 11.4. I assume that's volumetric effects of, if you're looking through something that has some impact on that. Small structure bundles them together, helps shorten the length of the parameter lists for camera constructors. We will only include the camera's constructor prototype here because its implementation does no more than assign the parameters to the corresponding member variables. So camera base can implement a number of different methods. A number of the methods required by the camera interface directly, thus saving the trouble of needing to redundantly implement them in the camera implementations that inherit from it. So, for example, we got film interface for getting film and also getting the camera transform. So sample time method is implemented by linearly interpolating between the shutter open and close times using the sample U. That's probably uniform random. Provides a generate ray differential method that computes ray differential via multiple calls to a camera's generate ray method. Okay, so it's just going to be generating one ray and then some neighboring rays to kind of judge that differential there. One subtlety is that camera implementations that use this method must implement the camera generate ray differential method themselves, but then call this method from theirs. Note this method signature is different from that one. Cameras pass the this pointer as a camera parameter, which then which allows it to call the camera's generate ray method. This means this additional complexity stems from our not using virtual functions for the camera interface, which means that the camera base class does not on its own have the ability to call that method unless a camera is provided to it. This primary ray is found via first call to generate ray. If there's no valid ray for a given sample, then there can be no ray differential either. Okay, so two attempts are made to find the X-ray differential. Sorry. Yeah, one using forward differencing and one using backward differencing by a fraction of a pixel. It's important to try both of these due to the vignetting at the edges of the images formed by realistic camera models. Sometimes the main ray is valid, but shifting in one direction moves past the image formed by the lens system. In that case, trying the other direction may be successful in generating a ray. That's interesting because it's in raster stuff. When you look at the differentials and stuff, they're within the what is it, a 2x2 block kind of thing. So that is interesting because it makes sense that what they're talking about, the vignetting on the external occlusion inside the camera system. That's cool. If it was possible to generate the auxiliary X-ray, then the corresponding pixel-wide differential is initialized via differencing. Okay. And so you specify some epsilon that you're moving in either direction to get that differential. So implementation of the fragment. Find camera ray after shifting one pixel in the Y direction follows similarly and is not included. If a valid ray was found on both X and Y, we can go ahead and set up the has differential member variable to true. Otherwise, main ray can still be traced just without differentials available. Okay. Finally, for the convenience of its subclass, camera base provides various transformation methods that use the camera transform. We'll only include the ray method here, and others are analogous to this. Cool. That's the end of 5.1. I